Hello everyone. So let us start now. Okay. So going to talk about memories and chip design. And so I'll give you a brief introduction of evolution of chip design industry, uh, introduction to memories, different types of memories, memory hierarchy, memory controllers, and then we look at IP verification flow. Finally, we look at what companies are looking for when they hire fresh engineers, and we talk about the KDEM and the Triple IT Bangalore course. Okay, so we look at evolution of chip design. So, have you looked at the gadgets that you use all around? Few of them are shown in the images here, and all these gadgets contain multiple chips inside. Of course, you all know each of these chips today is called as a SoC. SoC stands for system on chip. System on chip. It's called a system because it contains a lot of hardware inside. A system on chip typically contains nowadays single or maybe multiple processors, multiple clusters of processors, large amount of memory, multiple I/O interfaces, and various other system peripherals. So these SoCs are small, powerful. They consume lower power, and so they help us with sustainability as well. So in this, we see that here we see a 5 MB hard drive in 1956 compared to 128 GB pen drive in 2017. Now I think maybe a terabyte might be available. It's a little old image here. So what we see here is so imagine the amount of storage that we've packed now and the amount of power saving that has been done, right? The amount of space saving that has been done. So this is the power of the chip design industry, how it is going to revolutionize our world. So here we see a supercomputer in 1967 on the right side with 36 megaflops. So megaflop stands for, it can do 36 mega operations per second. And you see the size of the computer, multiple people operating it, the amount of power it would have consumed, the amount of space it requires. Whereas we see here the NVIDIA Tegra chip in 2015. We're today in 2023. This would have also evolved further now. So this Tegra chip has about 1 teraflops. So this is 1 tera operations per second. Okay, now we look at the terminology of how we call it VLSI. So in the initial days, there was SSI, which is small scale integration, about 1 to 100 devices. Then medium scale integration, which is 100 to 1000 devices. Then large scale integration, 1000 to 1 lakh devices. Then VLSI, which is 10,000 to about 1 lakh devices. And VVLSI is more than 1 lakh devices on the chip. And then people call it sometimes ULSI as well, right? All of it said and done, it's all chip design. Okay, so moving to the next chip. So there was this Gordon Moore, who was one of the founders of Intel, and he gave a statement which became to be called as Moore's law. I'm sure you will have heard of it. That he's predicted that every 2 years or 18 months, the number of transistors on a chip will double. And this became a norm that all the industry would run to meet this target, and it became self-sustaining order. Over the period, people started saying that Moore's law is dead and you can't pack more transistors in a single chip. But then companies came up with 3D chips trying to pack more dies, stacking one die on top of other, and which makes Moore's law to be still alive today. Okay, here's a graph where we see the transistors on a chip with respect to some years. And so here you see that the Pentium processor, which was launched around in the 90s, it has about between 1 million to 10 million processors, 10 million transistors. That time it was a very large chip. Nowadays, the chips of today, the SoCs of today are much, much more complex and more big. So here we change gears and look at memories. So what is a memory? A memory implies something place where you store information. Okay, in the electronics world, where you store information is more appropriate, right? So all computers, mobile phones, all devices around you have a lot of memory. Without memory, we humans also cannot function. It's an essential part, and the same way with these machines that are being built. Okay, in electronics world and the chip design world, we call memories in bits, bytes, kilobytes, megabytes, gigabytes, terabytes, and so on. Here is some classification of memories into different types. So there is a primary memory and there is a secondary memory. So the primary memory is typically the memory which is used for most of the internal computation by the computers. It can be RAM, it can be ROM, and they are further divided into static RAM, dynamic RAM, and then the ROM can be programmable ROM, erasable and programmable ROM, electrically erasable and programmable ROM. Then there is secondary memory. This is typically the memory where you fall back when you want to save a file. So these are the hard disks on the computers, your magnetic tapes, your CDs, your DVDs, etc. Right? Then there is cache as well on the computer, and there are registers as well. So cache is used by the processors for fast processing, and registers. An example can be your parallel in, serial out, your serial in, parallel out, and so on. We'll look at some of these memories in more detail. So here we say that what is memory versus storage? This is essentially the memory is a bigger term and storage is typically used for the secondary memory. The memory where you save your files, these are the floppy disks in the olden days, now hard disks, SSDs, maybe flash drives, and typically the storage is non-volatile. That means it will not get erased till a large amount of time without power. Okay, now we look at the primary memory. So we discussed primary memory is typically of two types, RAM and ROM. So RAM stands for random access memory. In this primary memory, when the power is taken away, the RAM will forget the data, and the ROM will save the data. Okay, and the RAM is typically a fast access device, and this is typically used for all the computers. So you buy a computer today, a laptop today, you say, oh, my laptop has 4 gigabytes of RAM. So this is the RAM that we are talking about, which is the primary memory. Okay, so here are some differences between the RAM and ROM. So RAM is definitely is volatile, and ROM is non-volatile. There can be different types of ROM, like we discussed, which can be programmable ROM that you can program it again. There can be electrically erasable and programmable ROM. So typically RAM is faster than the ROM, and that's why RAM is mostly used for the internal computation by the processors. On all computers, all laptops, all mobile phones, every device has a sizable amount of RAM to for their internal computations. Okay, like we say, secondary memory, the storage, the typically the non-volatile memory. This is the hard disk drive (HDD) that we call. Nowadays, people are moving to SSDs because SSDs are much faster. These are the solid state drives. Then we have the optical drives, the DVDs or the CDs, which are becoming obsolete nowadays. Then we have the tape drive. This is typically very low cost memory. You used to store data in magnetic tapes. And this is slower storage. And nowadays, some companies might be using this for backup, but typically not being used much. Okay. Then storage array is another data storage system containing multiple disk drives. So you can have a array of disk drives, and you can call it a storage array. So secondary memory is permanent. I will say kind of permanent because it doesn't stay forever. It can store data even when the power is not there. right? So it keeps the data in it with itself for quite some time. So you practically can call it permanent. Okay. So moving on, now we look at what is cache. We saw other than secondary memory, there is cache. So cache is typically a memory in which the CPU uses it for faster computation. There can be multiple levels of cache memory: L1, L2, L3 cache. So you see this memory is closest to the CPU. The CPU first talks to the cache, and the controllers around the cache will bring data in from main memory into cache, because access to the main memory, which is the primary memory, is typically slow uh, compared to the requirement of the CPU. And so the cache is somewhere the processor and the other controllers will try to bring the data into the cache for fast access by the processor. And if the data is large and cannot be brought from main memory, then there is a secondary storage from where the main memory will be loaded. Okay, so let's move on to the next slide. So like we discussed, there is L1 cache, L2 cache, and L3 cache. Out of this, L1 cache is the fastest and closest to the processor. Then there is a level 2 cache, which is a little far from the processor, and it talks to the L1 cache. And then there is a L3 cache, and which talks to the main memory. So processors will typically use cache for creating a kind of a buffer for usage. Now this buffer is required, so there can be a data cache, there will be a instruction cache. So processor, what it will do is that, let's take an example that processor is executing a set of instructions. What it will do is it will bring maybe next 25 instructions or so, 24 instructions or so into the cache memory. And it starts executing very fast one by one, right? If it tries to access them from the main memory at the runtime, then it becomes slow. It has to wait for the cache for the instruction to come. So it keeps them. And when there is a jump instruction, which comes in the code, then the processor discards that cache line and tries to refill with the new location from where it has to jump. Okay. So in this we see that some typical sizes of the cache are also mentioned. So L3 cache is typically the largest, L2 is smaller, and L1 is even smaller. Okay. So advantages and disadvantages of cache memory. Cache memory is typically quite costly and is the fastest memory on the chip. Okay. And this is typically created by static RAM. And of course, you want to keep it limited storage because it is quite costly. Okay, here is what we look at as a memory hierarchy. Okay, so at the top you see is the CPU, then there is a processor register. So these are the registers of the processor which are very fast access. This is also static RAM typically, or maybe created by flip-flops. So these registers are like the registers of the ALU inside the CPU, and they are natively available for the CPU processing to access these register values. The next is the CPU cache, which is also quite fast memory. Again, we saw L1, L2, and L3 kinds of cache. Then beyond that is the physical memory. In the physical memory, we have random access memory, which is the RAM. It can be static RAM, it can be DRAM. Typically, based on the cost, it is SD-RAM, which is synchronous dynamic RAM, or you can have a DDR RAM. Typically, all computers today use DDR. So every DDR has a spec to it, has a speed at which it can function, and it's reasonably fast, slower than the cache definitely. So DDR is much cheaper compared to the static RAM. Then we have the solid state drives or the hard drives in the computers. This is non-volatile memory. And then beyond that is the virtual memory, that if you want to keep it even bigger, if you want even bigger memory, then you can have slow and cheaper memories available. This can be the mechanical hard drives or the tape drives that we spoke about. Okay, so memory usage around us. So we see computers which have significant amount of memory, mobiles, printers, digital mobiles are today being marketed with the amount of RAM they have. Printers also have a full system and memory, your digital cameras, your DVD players, and all the appliances around you which you see have significant amount of memory. And they typically have primary memory and secondary memory as well. So the secondary memory typically can be smaller because there is no user trying to access that secondary memory, but only being accessed by the operating system and the applications inside those devices. Okay, so now we look at an IP verification flowchart. Okay, now what is IP verification? Let's say you have a memory controller you want to verify. A memory controller. Okay, let's look at what is a memory controller first. A memory is a design which functions based on the parameters that, okay, when you want to write data, it says, okay, you keep your data stable at my data bus for so much long time, and then we will be able to save data. But when you do digital design, you have a clock. You don't work on time, right? So based on the mapping of the memory, when you say, okay, for so much time we will keep the data stable, so that means maybe one clock, maybe two clocks, maybe three clocks, right? That's how you create a controller. So controller will take care of what data will get stored inside the memory and how to read and write from the memory. So the goal of memory controller is to free the processor from the nitty-gritties of the memory operation. Okay, so if you're going to verify a memory controller here, that's the IP or the DUT or the device under trust. So you look at first is we need the IP specifications, the specifications of the controller in this case, the IP interfaces. What is the interface of the controller? There will be an interface at the memory side. There will be an interface at the processor side. That processor is going to tell this is the operation I want to perform, and the data along with it. Maybe a read operation, it will fetch data, and maybe a write operation, it will get data from the processor. And then we look at, so first goal is to create a verification planning, wherein we create a spec tag test plan. We see if there are any compliance tests mentioned by any standard bodies, and then we see how we can do randomization. Okay, so then we create the IP verification plan. Then we create an architecture or of a test bench under which we want to verify the IP. Okay, and then we create a coverage plan. So coverage plan actually tells you that these are the points that we must cover in our verification. Whether your test has executed these scenarios or not, the simulation tool will tell you that this is covered or not covered. So coverage actually tells you how good it's a metric to tell you how good the quality of your verification is. Okay, so then you create a test bench and you create a test environment around it. You create test cases and sequences in some cases when you work with the SV and UVM. And then then you run those test cases. If you have failures, you will debug the test cases. If the test cases pass, you move to the next test case, and then you make a decision that I'm able to meet my sign-off coverage or not. If sign-off is okay, then you say, okay, my verification is complete. If not, then you go back, maybe add more test cases to understand what are the holes that you want to cover in the coverage, which is not getting covered. Okay, this is the high-level IP verification flowchart. Now let us move forward. So this is a memory controller. We talked briefly about a memory controller here. So the processor needs to access specific parts of the memory, and the memory controller tells the processor where the data is stored. So typically the processor needs to be freed from the nitty-gritties of the different types of memory. The memory is a SSD versus a HDD or versus a CD or versus a DDR. The processor need not be worried about it. It just says, I need to read data from this address, and the memory controller has to fetch it. Similarly, it says I need to write data at this address, and the memory controller has to write it. So the goal of memory controller is to act as an interface between the processor and the memory, right? So this is a block diagram where we see RCDs. This is for the DDR. There is a data buffer and there is a RCD for RDIMM and LRDIMM uh, type of memories and memory controllers. Okay. So now I think we switch gears and we look at, uh, why would you want to choose the VLSI industry? Okay, this is actually the real where the real electronics is being done. Today's myth in the industry is that AI is all software. AI begins with hardware. There are so many customers of ours and so many companies in the world who are creating AI chips. So without chips, the AI software does not work, right? Then it's a $550 billion industry globally today and growing at a steady pace. We see that the amount of electronics in every device in the aeroplane, maybe the automobile or the scooter or maybe your mobile phone or maybe your wristwatch is increasing day by day, right? Do you know that there are about quarter million of sensors on one wing of an aeroplane, right? All the goal of these sensors is to make sure that this wing is working well, right? So that's how you can see how the electronics industry is scaling, and all around us for the safety and security and for next level of achievements to be done. And till the time then when we have the next chips to be planted in humans as well. Okay, salary packages for freshers begin from 5 lakhs to 12 lakhs. And after 5 years, you can expect 24 to 30 lakhs. Nowadays, I would say maybe more. Uh, Already, VLSI industry is short of workforce. There is requirement of about 10 to 20,000 engineers in India, and I think the Indian requirement is close to 1 lakh engineers in the next 5 years. But most of the engineers today are looking at the software industry, and everyone moves to the software side. So anyhow, it's a quite a lucrative industry to work in, and quite challenging, interesting as well. This is about the growth of the chip design market globally, given by GSA. So it is expected that it will cross about $820 billion market by 2028. That's about maybe 5 years from now. It's not very far. Okay, so there is, I think some slides are got mixed up somewhere. So what is the verification IP? The verification IP is a IP which is used to verify the DUT, which is the device under test. And what are the advantages of using a verification IP is that it has pre-created test cases. It has pre-created models to test the DUT. If the DUT is a memory controller, it will have models through which the processor will write. Let's say this is AXI bus or APB bus, and it will have models to mimic the memory. It will have all the models around it, and it will have algorithms or checkers around it to see whether the protocol is being followed correctly or not. It does end-to-end data checking with scoreboards, and it really helps to reduce the time to verify. It gives you coverage information that this much is covered. These are the coverage points that must be checked, and so on. And it's quite generic and easy to use. Okay, so we were looking at the chip design industry. So here we look at from a fresh engineer's perspective, what are the shortlisting methods being used by companies? So it's not specific to any one company. These are generic guidelines I created. So first of all, companies see that okay, there are so many thousands of engineers available to be hired today. So how do I shortlist the best? So some companies will create a minimum percentage guideline that okay, I will hire anyone who has at least this much percentage. Then some companies, what they will do is they will say, okay, let's restrict the colleges from where we've got good results, and we want to continue with them. right? So they identify their colleges with whom they hire from, and they say, okay, other than these colleges, we will not hire. Okay, then beyond percentage, still companies see, okay, there are so many engineers, and how do I get the best people, right? So they look at the CVs and do some kind of screening. Maybe they look at projects that you have done in your engineering or after engineering, right? And they, if you've mentioned your interest areas, what are your interest areas, and what you have done around those interest areas. Based on that, some level of screening is done. And once the CVs are screened, to get the best candidates, companies will do written tests followed by interviews in some cases. Okay, and the key points of selection will be aptitude, engineering basics, communication skills, and knowledge or skills in the line of work that the companies are doing. Okay, so what actually the companies are looking for, they're looking for really passionate engineers. That's the number one thing. Number two thing that companies are looking for is in the engineers is the right aptitude. This is one of the most important things, over a period of time that we realize that aptitude is important, but attitude, with the right attitude, one can beat somebody with a better aptitude. Okay. And companies also look for good aptitude, definitely. Then again, companies are looking for how much learning time will be there for the new engineer and how soon they can become productive. Okay, how can we reduce the time for training? Okay, so the major skills that will help to reduce the training time from a semiconductor industry perspective, and more specific to verification or digital verification or functional verification today. Okay, so good conceptual understanding of digital electronics, including combinational, sequential, all kinds of state machines, and so on. C programming is something which is very handy and useful. Then you have knowledge on HDLs, Verilog, VHDL, knowledge on system Verilog, which is a high level verification language today, and verification methodology being used today is UVM. Everybody is using UVM across the globe. And then if somebody has this knowledge, and beyond that, if you have protocol knowledge, some basic protocols that you can study at your end can be APP, I2C, UART, SPI, etc. And then there are some mid-level protocols, a little more complex than these would be AXI, AHV, or I3C and USB2. Right? So if you have knowledge on these things, then the companies feel, okay, this guy is quite ready to be used. In the company is more useful, and the training time is less. Okay, then in the last, I want to talk about briefly about the course which has been launched by Karnataka Digital Economy Mission and IIIT Bangalore. This Futurewiz is a training partner, and IIIT is also a training partner. This course has been put together with the right industry connect, and the course curriculum is designed by the industry. Basic concepts in this course are being taught by IIIT Bangalore, and the course is supported by the industry. It is highly subsidized by the Karnataka government and makes it a really very useful course. It will help you to learn with the usage of the industry leading tools. Right. So I request you to, if you're looking for a career in the chip design industry, it's maybe a very good learning platform for you. Please go ahead and apply for this course at Karnataka Digital Economy website. Okay, the link is mentioned here. Okay, that's all I had for today. Thank you so much. We can open up for some time for questions. Do you guys have any questions? Please write it in the chat box. Okay, I see something's coming up in the chat box. Okay, I see few messages on the chat box, but no questions. Okay, Samir is asking, as the market is down, when can we expect the openings? Okay, See, Samir, market is down. That is something not in anyone's control. That's probably what God can control, I feel. But if you have the right skills, companies are hiring even today, maybe selectively, but companies are hiring today. And I feel that maybe next quarter hirings will open up again. So this quarter also hirings are being done. There are companies I'm aware who are hiring this quarter as well. How long the training will be there? This is a 6 months training course. There may be a 3 months internship after that as well. Initial part 2 months will be trained by Triple IT Bangalore, and after that 4 months of training is given by Futurewiz. Okay, Soumya is asking the course that you mentioned, is it online or offline mode, and how can we apply? You can search for k-vlsi and kdem on the web. I mentioned the link, and the course requires full time for first 2 months. After that, it is hybrid. It is not fully online. Okay. So which course is better, front end or back end? Both courses are good. Any one area you have knowledge is really very good and very impressive. Both front end, back end, both are required in the industry. Now, there are too many questions coming up. I have 1.5 years experience. I have AXI, PCI, knowledge protocol. As per what should I expect to add? See, if you already have experience in the industry, then I think you are already part of the industry, and you are looking for a switch. You can apply to multiple companies. AXI and PCI protocols are very good, but just having knowledge may not be good. You people look for depth of knowledge, and companies will also look for depth of knowledge in the concepts around digital electronics, around system verilog, UVM, and so on. Okay. That just answering straight from the book questions may not fit the bill. Companies will ask tricky questions which somebody who has really worked on it will be able to answer. Okay, then which is more in demand, automation chips or chips used for computers? See, automation chips. So the world has moved beyond automation, right? The world has moved to AI chips. There are AI inference chips, there are AI training chips. And all these chips are also going onto the computers, right? Computer chips are also in demand. Mobile phone chips are also in demand. Tablet chips are also in demand. And similarly, for a host of other devices, now smart watches are there, they are also in demand. So all these chips are in demand. And when you work on chip design, it's not necessary that you stick to a particular domain. You can work on automobile industry. Automobile industry is also growing very strongly. This is the biggest growth area is automobile today. Okay, let's move to the next question. The next is for entry-level DV engineer, how memory controller projects will be helpful. Memory controller, if you have good knowledge of DDR, it's a very strong protocol. If you have good knowledge of memory controller design or verification, it will be very useful. You don't get that knowledge so easily in the market. It'll be pretty useful. Okay, if we have IT industry experience, will it be counted while placement? It will be counted, but not fully, because this industry is different. But you definitely get the maturity from any experience that you have, that you are able to pick up faster. So it will be counted, and different companies may count it in different ways. So there is no one answer for that. Okay, so have we answered most of the questions? Uh, what is the future scope of ES? Embedded systems. Embedded systems is also growing at a very fast pace. There are huge requirements in embedded side, so there is no doubt about that. The chip industry is growing, and with that, the embedded systems is also growing. In memory controller, now memory controller is not an organization, right? So do they teach us coding as well? So memory controller is not an organization to my understanding, right? So if you want to learn coding, wonderful. In this KDEM course that I'm talking about, there will be coding that will be taught. Coding for, to some extent, design and verification both will be taught. Yeah, architecture design will also be taught, but at a high level, and architecture of the memory controller can be provided, and you can create your own memory controller. Okay, what skills should be learned with the markets will be open? What extra skills should be needed for entry level engineering? I already showed in the skills that will be required in the market. I showed the skills that are required. That will be great if you have those skills. So these skills are system Verilog, UVM, uh, digital electronics, Verilog, VHDL. But you need to have depth of knowledge in these topics. If you know any scripting language, even better. You know any protocols, even great. What about fee structure? I think the fees is about 15,000. Please go to the website and check it out for yourself. IP verification knowledge must for 1.5 years. So 1.5-year person can have IP verification knowledge, can have SOC verification knowledge, can have subsystem verification knowledge, can have knowledge maybe on backend, can have knowledge on DFT, can have knowledge anywhere, right? So depends on what you've done in these 1.5 years. The domain you have worked on in 1.5 years, you should be able to, write more about it, maybe talk more about it or explain more about it to the companies. Okay, so thank you all. Uh, we will wrap up the Q&A session now. Thank you. I wish you all the best. Thank you. Thank you for your time to attend this webinar. Thank you. Bye bye.